Hello, my dear students. Welcome to the IMS GATE Academy. How are you all? So, guys, please reply. Are you enjoying GATE Score Booster session? Just a second. Okay, MTMM, good sir. Okay, great. So, as you know that Prashant Kumar, good sir. Okay, great. So, as you know that uh, in the yesterday session, I have taken the electrical machine subject. Means we have started the electrical machine subject in which the chapter 1 and the chapter 2 has already been covered. So, which chapter? The transformer. Yes, sir. Enjoying. Great. Excellent. So, please do not forget to hit the like button, and to mark your attendance, I want you to hit the like button. All right, sir. Enjoying. Great. Excellent. So please inform your friend and the student community wherever you are connected with the social media to join the session as fast as possible. Definitely we're going to have a live session as a good manner. All right. So please inform your friend and the student community wherever you are connected. All right. So as you know that I have already taken the session 1, or you can say the part 1 of the electrical machine, and in that we have covered the transformer and the induction machine, which is common for electrical and iron. All right. So we already covered almost 8 marks. We almost covered the 8 marks when it is considered to the electrical stream, and for the iron stream we have covered almost like a 6 marks, you can say. All right, so in this session, which is a part 2, we will going to see the question related to the remaining chapter, that is DC machine and the synchronous machine. All right, so how many of you are eagerly waiting to start the session? Guys, do fast reply, and please subscribe the channel as well, so that you will going to get the wonderful session that we are conducting. All right, and also press the your notification button, such that you will going to instantly notify whenever we are going to live in our YouTube channel. All right, so shall we start? Saurav Upadhyay, Nikhil sir is the best. Thank you, Saurav. Thank you for the appreciation. All right, so shall we start the session? So let us directly, and this is the part 2 now. Those who have not watched the past one, that the part 1, after the session will going to be over, please go and watch those sessions. All right, and we have almost covered the 30 to 40% of the electrical syllabus. All right, means your network and control system and mathematics, that all subject has already been taken. All right, so high level of energy. Thank you, Pragyavad. So we have already covered your 30 to 40% of this of the overall syllabus when it is compared to the electrical stream. All right, eagerly waiting for the session. Enjoyed the last session. Thank you, Vipin. Very interesting question. All right, so definitely you are going to see more interesting, more interesting question in this session. All right, definitely we'll going to see. So in this session, as I told you, that we have a DC machine chapter and as well as synchronous machine chapter. So first we will start with the DC machine and with some great question, and after that we'll move on to the synchronous machine. All right, so shall we start? Shall we start? All right, so this is the DC machine a chapter in which these topics are very important. All right, so if you see the past year question, now definitely you will come across that whatever question till date we have, those are framed with this topic, you can say. All right, so in that, torque, EMF, losses, efficiency, operating characteristic of DC motor, this is very important. And one more important topic is speed control, means whatever question till date we have, those are framed with this topic itself. All right, so let us move ahead with the next with the very first question. Shall we start? एक बार आग लगा देंगे, मतलब चैट बॉक्स में. Shall we start? All right, so let us see the first question and I will give you some time to solve this particular question. All right, so this is the very first question of the today's session. All right, a 250 volt 25 kilowatt shunt motor has maximum efficiency of 89% at shaft load of 20 kilowatt and speed of 850 rpm. The field resistance is 125 ohm. Calculate rotational loss and armature resistance. What will be the line current, speed and the efficiency at an armature current of 100 ampere. All right, so let me give you 2 minutes for this. Unmatchable energy. Thank you, Saurav. So guys, please do solve this question. If you are able to solve this question, definitely you will going to have your 100% marks in DC machine. Meanwhile, let me move aside. If you want some help, then please let me know. If you want some help, then please let me know. 1.5 minutes remaining, fast. What do you mean by maximum energy, maximum efficiency? What the first thing will come to your mind or strike to your mind when it comes to the maximum efficiency? If you know this, then definitely you will have your answer at your fingertip. So 1 minute remaining, fast. I'm seeing that the like are very less when it is compared to the number of viewers. So please guys, please mark your attendance by hitting the like button and also do subscribe the channel so that you will going to have or enjoy the wonderful session. Definitely will going to enjoy whatever session we are going to be conduct in future. Half minute remaining, fast. All right, so time's up. Do we have the answer? Any tukka for this question, for this particular question? All right, so here one important thing, that is maximum efficiency. All right, so this maximum efficiency is a very important statement for this question. Now with the maximum efficiency, what we can understand, the maximum efficiency says that whenever your variable loss becomes equal to the constant loss, then your efficiency will going to be maximum. Variable loss is what? Copper loss, which depend on the load, so which is basically a copper loss, and the constant loss is what? Those losses which are not depend on the load. All right, so this is given as 89% efficiency, but this is occurring at 20 kilowatt at a speed of 850 rpm. The field resistance is 125. Calculate rotational loss and armature resistance. This we need to calculate. What will be the line current, speed and efficiency at an armature current of 100 ampere? All right. Shall we move ahead? All right. Now, first, let us understand the power flow diagram of the DC motor. As this question is regarding the DC motor, and we know that in DC motor, the electrical will be the input and the output will be the mechanical. All right. So this this electrical will be your input, Vt into IL. This is input power. Now after that, we will be having the armature. All right, we will be having the armature. So those armature will give you the ohmic laws together with the field resistance. So the ohmic laws are consist of this all parameters. All right, armature laws, shunt laws, series laws, and the brush laws. All right, so these all losses are known as ohmic losses. And after that, between the between the all right. So where we were? We were about to calculate the all these things. So maximum efficiency is given as 89%, and the shaft load is given as 20 kilowatt, speed that is given, and field resistance, that all are given. We need to calculate the rotational losses and the armature resistance. All right. So let us move ahead. This is the circuit diagram of the induction, sorry, not an induction motor, DC motor, and the power flow diagram that we have already seen. Now, this is what? This is a DC shunt motor. All right, this is DC shunt motor, where this is a load, it is basically good to say that this is a supply voltage or a terminal voltage. All right, this is a terminal voltage. So this V, and from here this will act as an input, that is electrical input, and the current will come here and it will enter like this. All right, and this is a field resistance or a shunt resistance, you can say. So what data we have? We have maximum efficiency. Let me write first as 98%, and this is occurring at a 20 kilowatt. All right, 20 kilowatt. Just a second. Okay, that's all. So here what will be the input? This shaft is what? Basically this is the output of your motor. So this efficiency is given here. So this efficiency implies that your variable loss is equal to constant losses. Done. Now what is efficiency formula? This is equal to output by input into 100%. All right, so for the maximum efficiency, the formula will be same, but we need to put the values. So this P output is what? Shaft power, which is 20 into 10 to the power 3 whole divided by P in. And efficiency is 98, so this will be 0.98. So once you solve this, you will get P input as, let me write it directly, 22471.9 watt. All right, so this data we got. So this power means whatever power is coming from the terminal, so that power is this one. Now if you look here, this V and IL, basically this is what? This is supply voltage. Let me remove this, otherwise you will get confused. Just a second. Okay, done. So this will be your supply terminal, and the current there is IL. So can I say this value P input is basically what? This is V into IL. Done. But in DC machine, we used to write the terminal voltage as VT. V suffix T. All right, VT. So VT into IL is equal to this 2241.9. So do we have VT in the question? Yes, this is VT. This is VT. So from here I can get VT into IL, or you can say directly 250 into IL. This is equal to what? 22471.9. So from here IL will be equal to, let me write the answer directly, 89.8876 ampere. Done. Now here what I am doing, I want to calculate the losses which is occurring in the machine during the maximum efficiency. Done. So this is IL. Next, if you see ISH, this is what? This is equal to VT, this voltage. VT is in parallel, directly it is parallel to the RSH. So ISH is equal to VT upon RSH. So we have VT as 250 and RSH as, do you have RSH here? Yes, field resistance, which is 125. This is 125 ohm. Done. So 125. So this is equal to 2 ampere. Done. So we have IL, we have ISH. So IA, which is equal to IL minus ISH. So IL and this is ISH. So subtract these two, you will get 87.8876 ampere. Done. So this will be your, you can say the current here. All right. Now, let me find here losses. So losses will be equal to what? Input power minus output power. So what is the input power? This is 2471.9 minus 20 kilowatt. So 20,000. So this is equal to 2471.9 watt. So this is the losses. Now this losses is what? This is equal to, this losses is equal to, or this losses is occurring at the maximum efficiency. So this losses is variable loss plus constant loss, or you can say losses. This is equal to 2471.9. Done. But at maximum efficiency, just a second, but at maximum efficiency, this variable loss is variable losses is equal to constant losses. So 2 times of constant losses, this is equal to 2471.9. Let us see, 2471.9. So from here, the constant losses will be what? This is equal to, take the half, 1235.95. Do we get the same answer? 1235.95 watt. So this is the constant losses that we are getting during the maximum power transfer. Done. Now this losses is again equal to the variable losses as it is given here. So what is variable losses in the question? Is this one, means the current IA and the resistor RA. Why this is not the variable loss? This loss is not variable because here RSH is fixed, VT is fixed. So whatever current ISH is present, that will be constant. So sometimes this loss VT square by RSH is treated as a constant loss because these two parameters are constant. So here the variable will be the armature current. So armature current here IA square into RA, this is equal to 1235.95, and we have calculated IA as 87.8876. 87.8876 whole square into RA, which is equal to 1235.95, and from here RA will be equal to, let me write the result directly, 0.16 ohm. So this is the armature resistance that we got by solving these values. All right, am I clear? Now here rotational loss and armature resistance we have calculated. So rotational loss is what? Basically these losses are consist of the mechanical loss and your core loss. So what is mechanical loss? Friction and windage loss. So whatever losses that we have calculated here, that constant loss is equal to variable losses. This is what? This is variable losses. All right, so this is what? This is variable losses. So constant loss is basically what here? Rotational loss. Done. Any doubt in this? Do we have any doubt? Just a second, guys. All right, my dear friend. So we have calculated all this value. Now, our next part is to calculate the efficiency and many more, but this is related to the current, which is 100 ampere. So how to calculate the line current, speed and efficiency for this current? See here. So we need to calculate for 100 ampere. So this is what? This is armature current. This is armature current. So let me write directly for IA. This is equal to 100 ampere. This is given in the question. But let me take this case as a second case. IA2. Why? Because we have this current we have given, and with respect to this we will going to find the efficiency and all kind of that. So this will be treated as a IA1. Let us say first case. This is IS2 and this will be IL1. Am I clear? Any doubt in this? So let me take this ISH1. But anyway, ISH1 and ISH2 will be going to the same. All right, my dear student. So let us find. So for IA2, the line current IL2, this is a line current which is equal to IA2 plus ISH2. So ISH2 and ISH1 both are same because RSH and VT are not changing. So here IA2 is 100 and ISH1 is 2 ampere and this is equal to ISH2. So line current will be equal to 102 ampere. Done? Now under this case, whenever you are supposed to find the speed, then my friend, you will come at one or you will directly jump to the one equation, that is EMF equation, whenever the question is related to the speed. So EA is directly proportional. This is no load EMF in the machine. EA is directly proportional to phi n, and in a shunt machine this phi is constant because this phi is directly proportional to field current, and here field current is what? Basically shunt current. So since shunt current is constant, your flux is going to be constant. Done? So can I say E is directly proportional to speed, so or EA. So EA2 divided by EA1, this is equal to N2 by N1. So in the question N1 is given as 850. Do you remember? This N1 is given in the question as 250. Where? Sorry, 850. This one. So this N1 is 850. We need to calculate the speed over here, and EA1 and EA2 are still unknown. So how we will going to calculate this? Just a second. How we will going to calculate this? Guys, please like the session and please share the session with your friend. We want the competitive, healthy session here. All right. So let us move ahead. How to calculate EA1? EA1 is basically equal. Let me calculate here in this portion. EA1, or you can say from here, this is EA. So if you apply the KVL here na, in this loop, so this will be VT equal to IARA plus EA. The resistance is inside the armature. All right. So VT equal to, or you can say VT equal to EA plus IARA. So VT is anyway constant. EA1 plus IA1 and RA is constant. All right. So from here we can calculate EA1, which is equal to VT minus IA1 RA. So VT is 250 minus IA1 is 87 point, let me see, IA1 is 87.887 into RA. RA is what? We have calculated RA is 0.16. 0.16. All right. In the same way, if you calculate EA2, or let me write the result directly here. EA1, I have the value EA1 as 235.938 volt. Done. And similarly, EA2 will be equal to VT minus IA2 RA. So when you solve this, you will get the answer as of EA2 as 234 volt. Done. Any doubt in this? Done. Clear? So we have EA1, we have EA2. Let us substitute these values. So 235.938, 234. When you solve this, we get N2 value as 843.02 RPM. 02 RPM. Clear, my friend? Any doubt in this? Any doubt in this? Done. So substitute these two values. Now what next? We need to find the efficiency at this 100%. Sorry, not 100%, at 100 ampere. So let me add the page. So efficiency at 100 ampere. So I want my output at 100 ampere and means that armature current, and input at this 100 ampere into 100%. So can I say output as input minus losses whole divided by P into 100%. What is input? Input is VT into IL2 for 100 ampere. VT is 250 minus IL2 is, sorry, not minus, into 102. All right. What next? What next? Do we have the answer? Guys, do we have the answer fast? All right, now see here. This input, let me rub this, sorry. This P input is again written as, or you can say this numerator part is written as EA2, I hope this is visible, IA2 minus rotational loss divided by P input into 100%. Okay, so how we will going to calculate this part? EA2 we have as 234 into IA2 as 100 ampere minus rotational loss that we have got na 1235.95 watt divided by, what is input here? 250 into 102 into 100%. So when you solve this, you will get the answer as 86.92%. 86.92%. Done? Clear? All right. So let me take you to the next second question, which is this one. All right. So let me give you 1 minute for this. Read the question and find the answer. Do it fast, guys. This question is very, very important because the frequency of this question is very high. If you see the question of the gate, definitely you will going to have this kind of question from in the DC machine. All right. So this question is very, very important, and definitely you will going to have a question from this topic, you can say, in gate 2023. All right. So this topic is very, very important. All right, do it fast. Time's up. So read the question. A 220 volt DC shunt motor takes 22 ampere at rated voltage and runs at 1000 rpm. Its field resistance is 110 ohm and armature resistance is 0.1 ohm. The value of the additional resistance required in the armature circuit to reduce the speed to 800 rpm when the load torque is proportional to the square of the speed. All right, so definitely we will going to have two cases. Whenever you are supposed to solve the DC question or the question related to the DC machine, then definitely you will have to frame two cases. Definitely, without having those two cases, you cannot able to solve this particular question from the DC machine. So how I am saying that we will going to have a two case. See, 220 volt, this is VT value, and this DC shunt motor, this means that the flux will going to be constant. By DC motor, unless and until the shunt or the field resistance is changed, until and unless shunt and field resistance is changed, the flux will going to be constant for the DC shunt generator or motor, you can say. And this is 22 ampere at rated voltage. This is IL1 and runs at 1000 rpm. Let me take this as N1. Its field resistance is 110. This is RF, and armature resistance is, this is RA. The value of the additional resistance required to add in the armature resistance. So let me take this resistor as RE to reduce the speed to 800. This is N2. Next, and your load torque is proportional to the square of the speed. This means that TL is proportional to N square. Done. So this is the diagram again for the DC shunt motor. Okay. All right. So what we have, case 1. We have VT that is given to me, which is 220 volt. This is VT, 220 volt, and IL1 is given as 22 ampere. Done. And N1 is given as 1000 rpm, and RF is 110 ohm. RA is given as 0.1 ohm. All right, so let me write the value here, RA as 0.1, and this VT, this is equal to 220 volt, and here IL1 is given as 22 ampere, and this RSH, or you can say here, let me write RSH here itself, RSH 110. This is 110 ohm. So again, we need to calculate the resistor. All right, and it is related to the speed problem. Definitely, you will have to find the EMF. So EA1, this is equal to, apply the KVL, VT minus IA1 RA in this loop. All right, in this loop. So this is proportional to N. Let me write it directly. All right. For the case 1, N1, it will become N1. So do we have VT value? Yes, we have 220 minus. How to find IA1? IA1 is equal to IL1 minus this current. What is this current? 220 divided by 110 into RA. RA is 0.1 and this is proportional to N1. And N1 is given in the problem, that is 1000. Done. This is EA1. Let me take it as equation 1. Next, what we need to find? The EMF for case 2. The EMF for case 2. Okay, so how to find the EMF from here? See, I have added the external resistance and I need to calculate this external resistance value. This value I need to calculate. Alright, so RF is 110 and this VT is 220 volt. RA is 0.1 ohm and this is EA is unknown. Alright, and this REX is added. Again, here we have 2 ampere ISH. This is RSH, this is ISH. So how to calculate here? Please let me know. Can we find IA2 value here? Can we find IA2 value here? Why I am saying this? Because EA2 is equal to V2 minus IA2. This time this is the armature current. Alright, armature current. And in armature current we have a resistor as RA plus R external. And this is we need to calculate. So here IA2 is unknown. IA2 is unknown. So how to calculate this? 220 minus IA2 is unknown. RA is 0.1 plus R external. So we have a equation or you can say the characteristic of the load. That is, the load is proportional to the square of the speed. So under steady state, load torque is proportional to, or you can say that electromagnetic torque is proportional to load torque. Again, very important relation. This relation is very, very important. All right. So load torque, this electromagnetic torque is what basically? This is proportional. This electromagnetic torque is proportional to phi into Ia. Phi into Ia. Since phi is constant, can I say T is proportional to Ia? So if you substitute this value here, so from this your Ia will become proportional to load torque, and load torque is proportional to n square, and your load torque is proportional to n square. So your Ia is proportional to speed square. Done. So IA2 divided by IA1, this is equal to N2 square by N1 square. So IA2 is unknown. IA1 is what? Do we have the value of IA1? I think we have as, let me see. Here IL1 is 2022, sorry, not 2022, that 22 minus 2, 20. So this is 20. N2 is given as 800 whole square divided by 1000 whole square. So from here IA2 will become equal to 16 ampere, 16 ampere. Done? Clear everybody? So we have IA2 value like this. Now next, substitute this value here. So EA2 divided by EA1, this will equal to, see, this will equal to, I have written na, this is proportional to n. So this is equal to n2 by n1. All right. So EA2 is what? 220 minus IA2 is 16. RA is 0.1 plus R external. See here, this part, this is proportional to N2. Done. Now, what is EA1 value? EA1, can we have this value here? Please let me know. This is 220 minus, or let me write the answer directly. This will be 218. This will be 218, which is proportional to 1000. Let me take this as equation 1, not this one. Okay, and this is EA1. All right, so from here and from this part, we will going to have the answer. So EA1 is 218. This is equal to N2 is 800 divided by N1 is 1000. So when you solve this, you will get R external value as 2.75 ampere. So the correct answer for this question is 2.75 ampere. Any doubt in this? Do we have a doubt? Guys, please like the session and please share the session with a friend. Do it fast. Do it fast. So let us move ahead with the next question. This, the third question. A belt-driven 100 kilowatt DC shunt generator running at 300 RPM on 200 volt bus bar continues to run as a motor when belt breaks, then taking 10 kilowatt. What will be its speed? Consider RA equal to 0.025 ohm and RF equal to 60 ohm. Done. And each VBD, this is a brush drop of each brush, which is 1 volt. Ignore armature reaction. Answer up to nearest integer. All right, ABCD, this is given. We need to calculate. All right, so guys, this is the diagram of the DC shunt generator. This is a generator where this current is IA, this current is IL, and this current is ISH. This is RSH. Okay, and this is VT. Ignore this load part, na? Ignore that load because we will going to have the supply there. Sorry, this is generator, na? Okay. So we need to consider there as a load. Okay. So load for the generator will be what? Electrical. So whatever load we have, that is the electrical load. So let me write the data for this particular question. Again guys, please remember, for the DC machine, question, we require two equation. We require two equation. The first equation is torque wala. Torque is proportional to phi into IA, and your EMF EA is proportional to phi into N. For the shunt machine, you can say, for the shunt machine. And for the series machine, this will become IA square, because in that the armature current and load current both are same. Sorry, that armature current and field current both are same. Anyway, so with these two equation, we can solve any question from the gate. So moving ahead, let me rub this. So in the question earlier, this machine is working as a shunt generator where this data is given. Now when the belt breaks, it run as a motor. All right. So we need to find the all those values. So case 1. When it runs as DC shunt generator. All right. So do we have the value here? Yes, I have the value. VT as 200 volt. What else? This speed for the generator, we have a speed given as 300 RPM. All right. Do we have OR data? Any else data? 0.025 is armature resistance. 0.025. And the shunt resistance is 60 ohm. This RF is what? Field resistance, which is 60 ohm. Anything else? Yes, brush drop is 1 volt. So we need to consider that. All right. Done. So I need to find the speed. Again, I require EMF wala equation. EA proportional to speed. Whenever you are supposed to find the speed, you will come across, you will directly come to or jump to EMF equation. Am I clear? And whenever you are supposed to find the armature current, then you will look for the torque equation. Done. So how to calculate this, yaar? How to calculate this? Okay. So apply KVL here. For the generator. Let me take for the generator as EG, means EMF for the generator. This is equal to IAG RA plus VT. So here IAG is unknown, means this current. IAG is unknown. So how to find this? IAG is unknown. How to find this? Now, for this we have a data as belt driven 100 kilovolt. This is a generator running at 300 RPM. So this is what? This is electrical power. So can I say VT into IL from this, or ILG you can say. Let me write ISHG also. This is equal to 100 kilowatt. Guys, please do not multiply with a factor 3 or root 3. This is a DC machine. We don't have a concept of a per phase value here. All right, am I clear? So we have a VT as 200, IG or ILG is unknown. This is 100 into 10 to the power 3. So when you solve this, you will get ILG value as 500 ampere. Done. So ISHG this is equal to VT upon RSH. So this is 200 by 60 ampere. 200 by 60 ampere. So here IAG, this is equal, this is generator. So IAG is equal to ISHG plus ILG. ILG is 500 plus 200 by 60. So 10 by 3. 3.33, I guess. This value is 3.33. So this will become 503.33 ampere. Done. So from here, EG will be equal to IAG into RA is 0.025 and VT is 200. So when you solve, when you substitute all this value, you will get EG as equal to 233.455 volt. Done, my friend? Clear? And this EG is proportional to the speed. So generator speed. Done. So 233.455. This is proportional to whether speed of generator is given to us. Yes, 300 RPM. 300. Let me take this as first. Now let us go to the motor part. Let us go to the motor part. So here RSH is again 60 ohm. V is what? Or you can say VT. This is 200 volt. And this time I need to calculate the speed. So definitely I require what? I require EM. This is equal to VT. This is motor EMF. VT minus IAM RA. So this time this IA will become IAM. This is ILM. And this is ISHM. So VT is 200 minus, here again IAM is again unknown. So for that what we require? We require extra data, and this is given in the question. When it breaks, the motor will run as a load of 10 kilowatt. 10 kilowatt. So this 10 kilowatt is what? This power is this power. So P is equal to 10 kilowatt. This is equal to VT into ILM. ILM. So from here ILM, this is equal to 10 into 10 to the power 3 divided by VT is 200. So from here we will get the value as 50 ampere na guys, 50 ampere. Now in the same way I can calculate IAM. How? This is equal to ILM minus ISHM. ILM is 50 minus 200 by 60, and this is equal to, do we have the answer? IAM, yes, we have 46.67 ampere. This question is very simple. This question is very simple. Just use the KVL, KCL and the EMF equation, which is proportional to N, and the rest will be your calculation part. All right. So from here, can I have the value of EM? Yes, I have. EM will be equal to 200 minus 46.67 into RA is 0.025. 0.025. All right. Now this EM is proportional to your motor speed. So this is proportional to Nm. So let me solve this. This value is coming as 196.833 proportional to Nm. Let me take this as equation 2. Clear guys? Now 2 divided by 1. What we get? Nm by Ng. Ng is what? This is 300. This is equal to 196.833 whole divided by 233.455. 233.455. So when you solve this, Nm will be equal to 252.94 RPM. Again a simple question but a conceptual one. Alright. So here again I have used the EMF equation and the KVL, KCL, nothing more than that. For all DC machine question you require these two parameters only. So let us move ahead with the next question that we have is MSQ. Now read the question. A 4-pole series wound fan motor runs normally at 600 RPM on a 250 volt supply taking 20 ampere. The field coils are connected all in series. Calculate the speed and the current taken by the motor if the coils are connected in two parallel groups of 2 in series. The load torque increases as the square of the speed Assume that the flux is directly proportional to the current and ignore losses. So I need to calculate the speed as well as current when the coils are wounded in two parallel group with two in series. How to solve this? Gopal Rao, very well explained. Thank you, Gopal. All right, now see here, again we have two cases. Case 1, when all 4 coils are connected in series. Now, definitely the question would occur in your mind, sir, how you say that we have a 4 coil? From here I can say 2 parallel group. This is a 2 parallel group, and in this 2 parallel group, 2 coils are connected in series. So this means that 1 coil and 2 coil, and here also we have a parallel path like this. Done? Amit Goyal, nice description, sir. Thank you, Amit. So from here I come to know that we have a 4 coils. Done. So moving ahead, these all 4 coils are connected in series like this. Done. Now this is what? This is the coil which is of armature. This is the coil which is of the armature. Now let us take the total number of turns, means whatever turns that we have for this coil, let us take T. So if the total turn is T, then the one coil will have T by 4 turn, isn't it? Am I clear? So 4 coil will have total T turns, then one coil will have T by 4, T by 4, T by 4 and T by 4. And T is what? Turns of a total coil. And exactly at this time, let me take the current, whatever the current that this coil are taking is IA1. Clear, my friend? Any doubt in this? So what I need to calculate? I need to calculate the load torque. All right. I need to calculate the load torque and the, okay, one data is given now. The load torque is increases with the square of speed. So I need to calculate where speed and the current. So as it is asking for the speed, then definitely we require EMF equation. Let me use different color. EMF equation is proportional to phi n, and this question is related to 4-pole DC series machine. All right. Done, guys? Please let me know fast. Do we have the answer? All right. So this is what? E proportional to phi into n. So what is phi? Phi is given by the field current. If the field current is high, your flux is high. All right. But here this flux is what? Proportional to MMF. Earlier we used to write the current IF. Earlier we used to write the current IF. But here I am not writing IF. Here I am writing MMF. Why? Because earlier we have a shunt motor. We have a shunt motor. In the shunt motor, the field resistance is same or was same. So because of that reason, your flux was constant. But here this is a series machine type. This is a series machine question, and in the series machine, your armature current and field current and load current all are same. So because of that particular reason, I have written MMF, and also we have a number of turns as a changing variable. Earlier the number of turns was same, means your MMF, your flux is what? This is proportional to MMF. In DC machine or in AC machine you can take. In DC machine or AC machine, your flux is proportional to MMF, and MMF is what? N into I. N is number of turns, not the speed. N here is number of turns. So in the previous question, or you can say in the last 2 or 3 question, we have assumed that your number of turns was constant. So because of that reason, we directly we directly written there flux proportional to I. But here the number of turns is changing, so we cannot write proportional to I only. We cannot write the flux to be proportional to I. All right, am I clear? So here flux is proportional to mmf, or mmf is what? N into I. N is what? Number of turns, not the speed. So number of turns here is how many? T by 4, T by 4, T by 4, T by 4. Means this flux plus this flux plus this flux, this flux. Or you can say mmf, 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 mmf. Add all this, you will get T into IA1. T into IA1. Done? Clear? Now what next? For the current, we again require one expression, that electromagnetic torque is directly proportional to phi into Ia. Phi into Ia. And in this case, electromagnetic one is proportional to mmf here. mmf here is F into Ia1. What is F here? T into Ia1. So can I say electromagnetic torque for the first case, this is equal to total number of turns T, Ia1 into Ia1. This will become Ia1 ka square. So one, and let me take this as, or what we can do, we can directly write, just a second. Okay, we can write directly here. See, your load torque is increases as a square of the speed. So under steady state, your electromagnetic torque is proportional to load torque. So electromagnetic torque is what? This is not a, this is turns. Okay, I have written here turns of total coil. So here T Ia1 square is proportional to, your load torque is proportional to square of the speed. So let me write it directly, N1 square. And this will be treated as a equation 1, or sorry, equation 2. Done. Now let us move ahead. Case 2. Okay, case 2 means what? When we have a two parallel coil, or two parallel path, in which each path we have two coils connected in series. So this will have T by 4 turns, T by 4 turns, T by 4 turns, T by 4 turns. Means each coil will have T by 4 turns. And let me take this time the armature current as Ia2. Since this T by 2 all are same, means the resistance will going to be same. So the current will going to divide into 2 equal half, Ia by 2, and here Ia2 by 2. Done? Clear? Now in this case, mmf flux as proportional to mmf. So in this case, mmf will be what? See here, mmf will be what? Ia2 by 2 into T by 4. Here mmf, let me write here, F is equal to T by 4 into Ia2 by 2, Ia2 by 2 into 2, because of this. Done? Because of this. And we have this mmf also, so into 2. All right, so total 4 mmf we need to add. This mmf, this mmf, this will going to give this part, and this mmf will also going to be equal into 2. So from here mmf will become T by 4 into, sorry, not T by 4, T by 2, let me write here, T Ia2 by 2. All right. So do we have speed given here? No, we need to calculate speed, and the current also we need to calculate. Let us see how we will find this part. Okay. EMF we have, okay, EMF we have, that I have written there. I think one part I have missed, na? F is T into I1. Okay. Here F is T into IA1. So here I have missed N1 part. Okay, I have missed N1. Extremely sorry for that. Okay, let me take this as E1. Okay, so moving ahead, E2 is proportional to phi into N2, or you can say here phi is this part, phi is this part. So E2 is proportional to T IA2 whole divided by 2 into N2. Take this as 3. And again from the electromagnetic torque is proportional to load torque under steady state. Under steady state, electromagnetic torque is proportional to load torque. So let me write it directly. What we have here, MMF is T by 2 IA2 square, T by 2 into IA2 square. This is proportional to N2 square, isn't it? This is proportional to N2 square. Please check fast. Done, guys? Done? Okay. So let me take this as equation 4. So how to calculate the current and as well as the part that we need to consider. All right. Now see here. Do we have any information regarding armature resistance? This is the field coil resistance. Now this is field coil resistance. Do we have information about RA? No. So we will ignore that part. We will ignore that part. Okay. So we'll ignore that part. So let me add a page over here. So ignore RA plus RAC. This is equal to 0. So this implies VT, this will become EA, which is 250 volt. This is given in the question. And N1 is given as 600 RPM. Is it given? 600, yes, that is given. And supply is IA1 is 20 ampere. And VT is given as, that is already written. All right. So how to calculate, yaar? So let me write 4 divided by 2. So 4 is what? T by 2 into IA2. T by 2 into IA2 whole square is equal to N2 square whole divided by. Equation 2 is what? T IA1. T into IA1 square equal to N1 square. This is N2 square. All right. So TT will be cancelled out. So IA2 square divided by 2. IA1 is 20 na? 20 square. Sorry. 20 square. This is equal to N2 is given in the question. N2 is given in the question. No. So let me take this as N2. And here we have, or it is better to write directly here. See, N2 this is equal to, N2 this is equal to N1 times of, N1 times of IA2 whole divided by root 2 IA1. Let me take this as equation 1. Sorry, equation 4 we have taken, equation 5. Next is what? Let us come to the EMF equation. Let us come to the EMF equation. So 3 divided by 1. So what is in the 3? T IA2 by 2 N2. T IA2 by 2 into N2 whole divided by T into what is equation 1? T N1 IA1. T IA1 N1. This is equal to E1. This is equal to E1. Sorry, this is E2 and here we have E1. Just a second. Okay, 3 and 1. All right. But if you closely observe the machine, we have a series resistor and you can say armature resistor as 0. This means that E2 and E1 will be same because we don't have any voltage drop across the winding. Definitely E1 and E2 both are same. All right. So if this is the case, then TT will be cancelled out and E1 and E2 are same here because of 0 voltage drop. We have taken na in case 1, sorry, Vt is equal to Ea. So for both the cases this will be same. So from here Ia2 N2, this will become 2Ia1 N1. So Ia2 N2, substitute N2 from here, N1 into Ia2 root over 2 Ia1. This is equal to 2 Ia1 into N1. So N1 and N1 will going to be cancelled out, and here Ia2 whole square root 2 into 2, so 2 root 2 Ia1 square. Let me add a page. So Ia2 equal to 2 root 2 into Ia1 square. So this is square Ia1 square. So from here Ia2 will be equal to 2 root 2 whole root into Ia1. What is Ia1? Ia1 is given as 20. So when you solve this, you will get Ia2. Let me write the answer directly. Ia2 will be equal to 33.635 ampere. 635 ampere. All right, and rest is speed. Rest is N2. N2 is what? N1, which is what? N1 is given in the question as 600. No, sorry, 600 into Ia2 33.635 upon root 2 into Ia1, which is 20. So when you solve this, you will get the answer as 713.52 RPM. All right, so this is given in option 713 and 33. So this is given in option A and option D. So this is the correct option for this question. All right. So let us move ahead, guys, with the next question. This is a very interesting. Sorry, this was a very interesting question. Definitely, in the GATE exam 2023, you may going to get the question from this variation. All right. So let us move ahead with this question. A 230 volt DC shunt motor has an armature resistance and field resistance as this. This motor drives a constant load torque. So this time the torque is constant and takes an armature current of 20 ampere at 20 ampere at 800 rpm. If the motor speed is to be raised from 100 rpm to 1000 rpm, then the resistance that must be inserted in the shunt field resistor is dash ohm. So we have VT shunt motor, RA is 0.4. Sorry, this is 230 volt. RA is 0.4 ohm. 0.4. RF is 115 ohm. And load torque is constant, TL is constant, and armature current at this time. Armature current at this time is 20 ampere. This is 20 ampere. And what next? Okay, so this is case 1. Case 1. So IA1, this is equal to 20 ampere, and N1, this is equal to 800 rpm. So I require the speed. Sorry, I require the shunt resistance. So definitely I require the speed. So for speed, we require EMF equation. We require EMF equation. This flux into N. All right, now this is the first case. So where ISH, this is equal to what? 230 divided by 115. So this is equal to 2 ampere. So here IL1, this is equal to 20 plus 2. This is equal to 22 ampere. Done. So EMF EA1, this is equal to VT 230 minus IA1 20 into 0.4. So this will be equal to 230 to 22 volt. So from here EA1 is directly proportional to phi 1 N1. Now this time the question definitely come to your mind that sir, earlier for the shunt motor you have written flux as a constant, but this time you have not making this flux as flux to be constant. The reason is we are inserting the resistor in field winding. So for that particular reason, if you are changing the resistor of the field winding, the flux will going to change. So this is the reason why the flux is not going to constant. All right. So we have this part. N1 is given 800. So this is 222. Or we can keep this one only. Okay, let me keep this as equation 1. If you require the other thing, we can find it later. All right, now moving ahead. For this case, we have inserted this resistor. Let us say this is R external in the field. So earlier we have this ISH1. This ISH1 is what? This is equal to 230 divided by RSH, or you can say VT upon RSH. And this flux 1, let us say flux 1 is proportional to ISH1. This we know from the working of the shunt machine, or you can say DC machine. All right. Now, at this time, when you inserted this resistor, your shunt current is now changed to ISH2. This is IA2 and here IL2. So this time ISH2, let me take this as case 2. When you inserted R external, this we need to find. So R, or you can say ISH2, this is equal to VT upon, see here everybody, RSH plus R external. And this is proportional to phi 2. Done? Clear? Now next, let us find the EMF equation. Let us find the EMF equation over here. E2 or EA1, sorry, EA2. This will be equal to V2 minus IA2 into RA. So we have VT as 200, sorry, let me check. We have VT as, what we have VT? 230. 230 minus IA2 is unknown and RA is 0.4. And this is proportional to pi 2 and 2. Done, guys? Done, guys? Clear? Let me take this as equation 2. This I have taken equation 1. This as equation 2. Now, under steady state, your electromagnetic torque is equal to load torque. What is electromagnetic torque? Phi into Ia. This is equal to what? Load torque. Load torque is given as constant. TL is constant. So this means that load torque is constant. So can I say IA2 phi 2 is equal to IA1 phi 1. If load torque is constant, so electromagnetic torque will also going to be constant. So IA2 is equal to phi 1 by phi 2 into IA1. Let phi 1, or you can say let x equal to phi 1 by phi 2. So your IA2 will equal to x IA1. Done? Now, EA2 divided by EA1. This is equal to what? 230 minus what we have? IA2 RA. RA is 0.4 that we have written here. 0.4. This is proportional to phi into N2. Okay, so it is better to write here phi 2 N2 whole divided by phi 1 N1. This is equal to 230 minus 0.4 IA2 and EA1 is what? 222, na? Let me check. EA1 is 222. Done? So phi 2 by phi 1. Phi 2 by phi 1 will 1 by x. This is equal to 230 minus 0.4 x times of IA1. Here x times of IA1 whole divided by 222. So we have N2. N2 as 1000 means the speed has increased from 800 to 1000. So N2 is 1000, x is unknown, N1 is 800. This is equal to 230 minus 0.4 into x. 0.4 into x. Sorry, into x into what is IA1? Do we have IA1 here? 20 ampere divided by 222. So From here we will going to have a quadratic expression as, see here, quadratic expression as 32x square minus 920x plus 1110 equal to 0. So when you solve this, you will going to get x as 1.262 and 27.4881. So we have two value for the x, but this value is not possible. Because this portion x will going to be very high, and if this will going to be high, your speed will going to be very, very high. If the flux is lower, then speed will increase, isn't it? Because flux means the speed and the flux, the relation are inversely proportional. So if we have so much greater value, x1 is what? Phi1 by phi2, and this is equal to 27 point, let us say 5. So your phi1 is equal to 27.5 times of phi2, or you can say phi2 is phi1 upon 27.5. So this value is very, very less than phi1. If it is so, then your speed has to be very high. Means if earlier it was 800, then for this particular x, you will you would be having like a 2000 or 2500 like that RPM. But this is not given in the question. It is given 1000 RPM. So it has increased to 200 RPM by 200 RPM. All right. So this is the reason why this is not possible. Let me rub this part. Okay. So what we have, x as phi1 by phi2, this is equal to 1.262, and phi1 is proportional to ISH, na? So ISH1 divided by ISH2, this is equal to 1.262. What is ISH1? VT upon RSH whole divided by, what is ISH2? VT upon R external plus RSH. This is equal to 1.262. So here R external plus RSH whole divided by RSH, this is equal to 1.262. RSH is given as, let me see, RSH is given as 115. Okay, so R external plus 115 whole divided by 115, 1.262. So when you solve this, you get R external value as, let me write it directly, 30.13. Clear, everybody? Please like the session, everyone. Please like the session and share the session with your friend. All right, so let us move ahead with the next question. That is this one. All right, so a 400 DC series motor has armature resistance of 0.25. What running at, I think there is some typing mistake. What running at this is when, sorry, this is when running at 1200 RPM, it draws a current of 25 ampere. When a regulating resistance of 2.75 is included in the armature circuit, it draws a current of 15 ampere. Find the speed and the ratio of the two mechanical output, assuming that the flux with 15 ampere is 70% of that of 25 ampere. All right. So this is a DC series motor. DC series motor, we have a terminal voltage as VT and EMF as EA and armature resistance as RA. Do we have the value of RA? Please let me know. 0.25. This is 0.25 ohm. And RAC is given in the question. Do we have RAC value? Okay. We don't have RAC value. Let me see. Okay, we don't have RAC value, so we need to ignore that part. We need to ignore that part, RAC value. All right. So when it is running at 1250, it draws 25 ampere. So IL is 25 ampere. So this is case 1. Case 1 means when regulating resistance is not included. All right. So in this case, N1 is 1000 RPM. Let me check, guys. Please let me check. This is given as 1000 or what? 1200. Sorry. This is given as 1200 RPM, and IL1, IA1 and I series 1, because this is series machine, na? This is series machine. So this all are equal, 25 ampere, and here this is 400 volt. 400 volt. Okay. So again, I need to calculate the speed. Calculate the speed and the ratio of the two mechanical output. So since the question is about the speed, definitely I require EMF equation. EA is proportional to speed, or this time N pi into N. Done. What next? Can we calculate EA1? EA1 is equal to VT minus IA1 times RA plus RAC is 0, na? So you can ignore this. RAC is 0 ohm. This is not given in the question, so we need to take a 0 ohm. So this time IA1 will be equal to, IA1 into RA. So RA is given in the question as 0.25, VT is 400. 400 minus 25 into 0.25. So this value will be is, let me write it directly, 393.75 volt. This is EA1. And from this expression, EA1, which is 393.75, is proportional to phi1 and 1. Let me take this as equation 1. Then, now let us go to case 2. When RG is equal to 2.75 ohm. Now, at this time, what data that is given in the question? Your phi 2 is equal to 70% of phi 1. This is given in the question, and what else? And at this time it draws 15 ampere. IL2, ISC2, IA2, this is equal to 15 ampere. All right. So EA2, this EMF, EA2, and this is RA, and this is RG. This is RG, and this is VT. Current here IA2. Earlier I have taken IA1, na? No, I have not taken. This is IA1. So exactly at this point, EA2 is equal to VT minus IA2. Here RG is included, so RA plus RG. So VT is 400. IA2 is 15, RA is 0.25, 2.75. So this is equal to 400 minus 45. This is 355 volt. All right. And again, EA2 is proportional to phi 2 N2. N1 is given in the question. See here. Yes, it is given. So EA2 divided by EA1, this is equal to phi 2 N2 phi 1 N1. EA2 is 355. EA1 is 393.75. 393.75. Phi 2 is 0.7 times of phi 1 divided by phi 1. N2 is unknown, N1 is 1200, let me check, 1200 RPM. So from here, N2 value is equal to 1545.578 RPM. Done. Very simple here. Again, I am using two equation, that is EMF wala and the KVL around this armature resistance. All right, clear? Now next, I need to calculate the mechanical power. So mechanical power is what? EA2 IA2 whole divided by EA1 IA1. So when you solve this, we have IA2, we have EA2, this is EA2, IA2 we have, EA1 and IA1, all are we have. So from here we get the value as 0.541. Done, clear? Excellent. So you can expect such question in the GATE exam. All right. Now let us move ahead with the next question. That is the last question in the DC from the DC machine. All right. So two DC shunt generator are rated at 230 kilowatt and 150 kilowatt, 400 volt. So this is terminal voltage VT. Their full load voltage drops are 4% and 6% respectively. They are excited to no load voltages of 410 and 420 volt respectively. How will they share a load of 1000 ampere and the corresponding bus voltage? All right. So this is basically what? Two DC generator. So here I have ignored the field resistance. All right. Since no information is given about the field resistance, so we can ignore that part. From here as well, from here. And this E1 is given as in the question 410. Let me take this E1 as 410 volt. And what next? 420 volt for the second. And this is I1 and this is I2. This is load current IL. Let me take the bus voltage as V. Let me take the bus voltage as B. Now this generator are rated at 230 and 150 with a voltage drop of 4% at rated value, at full load value. This means that whatever loss that we are having, that is only due to the resistance. That is only due to the resistance. So 4% of voltage drop, 4% of full load current into RA. So drop for machine 1. Voltage drop, this is equal to 6%, this is 4%, na? 4% of, see here everyone, voltage drop at full load. So this will be equal to IL2, sorry, not IL2, IL1 into RA1. Now how to calculate IL1? From this part we can calculate. This is the rated power of the first generator. So 230 kilowatt, kilowatt, this is equal to VT into IL1. What is VT here? 400 volt. This is 400 volt. So 400 into IL1, 230 into 10 to the power 3. So from here IL1 is equal to, let me write it directly, 575 ampere. If you solve this, you will going to get this value. All right. So voltage drop now become 4% of IL1 is unknown. Okay, so what we can do here? Yeah, one thing we can do. This voltage drop that is given in the question. This voltage drop is given in the question. How? This is with respect to full load current, na? And this is what? Full load drop, or you can say the full load voltage, not a drop, that is full load voltage. So this voltage drop is 4% of 400. So this is what? This is basically 4% of 400. So this is equal to 16 volt. So 16 volt, this is equal to IL1 into RA1. So IL1 we have calculated. So from here RA1, this is equal to 16 upon 575. This becomes equal to, let me directly write the answer, 0.027, 0.0278 ampere. Done. Okay. Now for machine 2, 6% of full load voltage drop. So this is basically what? 6% of 400. So this is equal to 24 volt. Now this 24 volt is equal to IL2 into armature resistance of the second generator, RA2. How to calculate IL2? The rated value is given for the second generator is 150. 150 into 10 to the power 3 divided by 400 into RA2. So from here RA2 is equal to, let me write the answer directly, 0.064 ohm. Done. So we have RA1, we have RA2. Now we can apply the KCL at this particular point. Let us take this as node A. Okay. And one more thing, load current is given as 1000 ampere. Okay. So this is 1000 ampere. So KCL at node A. So V minus 410, this is RA1 and this is RA2. V minus 410 divided by RA1 plus V minus 420, let me see, divided by RA2 plus IL. IL is 1000 ampere. This is equal to 0. So when you solve this, substitute RA1 and RA2, you will get V value as 393.647 volt. Done. And what next we need to calculate? We need to calculate the load shared. Load shared means we need to calculate I1 and I2. So I1 will be equal to what? Let me write directly, 410 minus V divided by RA1, and I2 is equal to what? See the direction, I1 direction. This is generator, na? So it will go from EMF to the terminal, EMF to the terminal. And I2 is 420 minus V divided by RA2. So I1 will be equal to 588.24 ampere, and this is equal to 411.76 ampere. You can also solve, you can also find this I2 value as total current IL minus I1, because I1 plus I2 is what? IL. So we have calculated I1 from here. We have IL that is given in the question. So we can find I2. So that is all about the DC machine. Now let us directly go to synchronous machine, and from here we will see some problem related to the gate exam, or you can say from the gate perspective. All right. So this is the important topics in the synchronous machine. So the topics are short pitch and distributed winding, losses and efficiency, droops, parallel operation, characteristics of synchronous machine, voltage regulation method, and power flow diagram. All right. So let us see the question 1 in a synchronous machine. A 420 volt 50 Hz 3-phase synchronous machine operates at rated voltage and at leading power factor of 0.5. Shaft power is 20 kilowatt and excitation voltage is 390. If per phase resistance is 0.5, the synchronous reactance of the machine is dash ohm. So first we need to judge whether this machine is a synchronous motor or a synchronous generator. So look at here, we have shaft power and excitation voltage. So this is EF. EMF, and this 420 is what? This is terminal voltage, which is VT. Okay, this value is VT. And this machine is operating at leading power factor of 0.5, whereas armature resistance is 0.5. So this is what? This is RA. And we need to calculate XS, neglecting mechanical losses. Now one thing for sure, everybody please look at this point. So from here we can going to judge whether this machine is a generator or a motor. Now for the leading, two cases will be possible related to the voltage. Either your EMF will going to be less than terminal voltage, or EF less than EF less than VT and EF greater than VT. So if EF is less than VT in case of leading power factor, then this is the case for the generator. Whereas if EF is greater than VT at the leading power factor, then this will be the case for the motor. From the armature reaction in the synchronous machine that we have discussed in the class. All right, at leading power factor, for the generator you have EMF less than VT. So look at the problem. Your EF value is 390, VT is 420. So the first condition satisfied. This means that this is a synchronous generator. Am I clear? All right. So how to calculate this? This is synchronous generator. All right. So this is EF. I hope this is visible, na? Yeah. So this is 3-phase. So how to calculate this XS? I need to require EMF, RA, and RA is given in the question. Na? This is equal to 0.5 ohm. And EF is given, means the magnitude. In the generator, this EF vector is equal to 390 at an angle del. Del is load angle. VT is given as, okay, this is delta or star connection, it is given in the question. No, it is not given in the question. So we will assume whenever connection is not given, we will assume the star connection. So this EMF will now become 390 by root 3. 390 is what? This is the line voltage. This is the line voltage. And this VT is equal to 420 by root 3. Take VT as a reference. All right. So How we can find? IA is not given in the question, but power factor angle is given, which is 0.5. All right, so cos phi is given as 0.5. So phi is equal to 60 degree, which is leading. All right, everyone, please see here. Please see here. We will going to take the help of this shaft power. Now, under steady state, whatever power that is developing is mechanical power, and we are supposed to get the mechanical power, the electrical power in case of generator. Means the input will be mechanical and output will be electrical for the generator case. Now, before this mechanical loss has to occur. But do we have any information regarding the mechanical loss? No. If no information is given, then assume P mechanical equal to 0 watt. If P mechanical is equal to 0 watt, then this means that P developed is equal to P shaft. Means at the turbine, whatever power is generating, that is equal to directly the developed power. All right. So developed power is what? EF into IA, and the angle between these two. But anyway, P shaft is given in the question, which is 20 into 20 kilowatt, 20 into 10 to the power 3. Now this is the active power. This is the active power. So from here, this power is developing. This power is developing exactly here. Done. So 20 into 10 to the power 3. This is equal to power loss across this element, IA square into RA, which is 0.5, plus the output power, which is electrical. So this is equal to √3. Mind you, this is the 3-phase power. So you need to take the electrical power also as a 3-phase. So here I forgot to multiply 3, because if you forget to multiply 3, it will become a single phase loss, you can say. So since you are taking 3-phase power, so multiply this loss with a 3 itself. Plus √3 into VT. VT is 420. This is per phase. Line is what? 420. Into IA is unknown. Into cos phi is 0.8. So from here you will going to have the quadratic expression as 1.5 IA square plus 363 point, just a second, 363.73 IA minus 20,000, this value equal to 0. Now when you solve this, you will get IA value as 46.188 ampere, and one value is, means the other value is minus 288.675. But this value is not possible because the direction of current will be reversed. Then in that case, the generator will work as a motor. So this is not possible. So here IA we have calculated. Now we need to find this excess value. How we will going to calculate, guys? Okay. So in the generator we have equation of EF as magnitude of EF as root over VT cos phi, VT cos phi plus IA RA whole square plus minus VT, or you can directly write VT sin phi plus IA excess whole square. So I hope this equation you have seen in the synchronous machine. Definitely you have seen. So this magnitude of EF is what? 390 by root 3 by root 3 because this is the per phase equation. This is the per phase equation equal to root over this Vt is 400 na 420 divided by root 3. What is cos phi? Cos phi is 0.5 plus Ia we have calculated 46.188 and Ra is 0.5 whole square plus 420 divided by root 3 into, now everyone look at me, this formula has been derived by considering the power factor as a lagging type, So if you want to use this equation for the leading power factor, then you will have to take phi here negative. For the leading case, the phi will be negative. All right. If the case was lagging, then phi will be plus 60. If the power factor is leading, it will become minus 60. So sine of minus 60, where sine of minus 60 is what? Minus root 3 by 2 plus Ia is 46.188 into xs is unknown. Clear, guys? So when you solve this, you will get xs value as, let me directly write it, 8.2883 ohm. Clear? If you have any doubt, then please let me know. All right, so moving ahead with the next question. Do we have an option for that? 8.2. Okay, so this option A is the correct option. All right, so let us move ahead with the next question, which is this one. The effective resistance of a three-phase star-connected 50 Hz 2200 volt synchronous generator. Okay, so this time they have given synchronous generator with an effective resistance of 0.5 ohm per phase, and this is star connected, and your Vt is 2200. So this is all our line voltage. Until and unless specified as a per phase value, you need to you need to take the voltage as a line voltage. On short circuit, a field current of 40 ampere gives, on short circuit, the field current of 40 ampere gives full load current of 200 ampere, and EMF of line to line of 1100 is produced on open circuit with the same excitation. The regulation at full load 0.8 power factor lagging is. Okay, so how to calculate? How to calculate, guys? Percentage voltage regulation is what? This is calculated between magnitude of EF minus magnitude of Vt whole divided by magnitude of Vt into 100%. All right, so please keep this thing in mind, that we need to calculate the voltage regulation by taking the magnitude only, not the angle. All right, and here speed and frequency has to be constant and with the same field current. So I require EF. Do we have Vt? Yes, it is given in the question. 2200, but that is a line voltage. So from here, magnitude of EF, this should be in per phase, minus 2200 divided by root 3 whole divided by 2200 divided by root 3 into 100%. All right. So if you are taking a line voltage, then your EMF will also have to be in line voltage. Otherwise, you will going to get the wrong answer. Done. So how to calculate, yaar? Okay. Now one thing for sure. the negative voltage regulation is not possible. The negative voltage regulation is not possible. The reason is, for the generator and lagging power factor, for the generator with a lagging power factor, your EF is always greater than VT. Whereas for the leading power factor and synchronous generator, your EF is less than VT. That we have seen in the question 1. All right. So definitely your answer is between between C and D. So let us find the value here. Now here we have a field current 40 ampere, field current IF is equal to 40 ampere, and it gives, under short circuit it will give it is giving 200 ampere. So this is IISc, which is 200 ampere. Now with the same excitation, means the field current is same, and under this your open circuit voltage is what, or you can say EMF is what? Open circuit VOC, this is equal to 1100 volt. This is line voltage, and for the star connection this is line voltage. For the star connection it will become a VOC by root 3. Now see here, from the voltage regulation method of EMF method you can say, or the synchronous impedance method you can say. All right, all are same. From the EMF method, the ZS, synchronous impedance, is given by the voltage under open circuit condition and the armature current under short circuit condition, but both has to be taken under the same field current. All right. So this two ratio will give you synchronous impedance from the EMF method or synchronous impedance method that we know. So we have VOC, but this is per phase. So since this is star connection and this is line voltage, so the per phase voltage will be 1100 by root 3. IISc is given as 200. So from here ZS, let me write it directly, 3.175. You can also check that, 3.175. All right. So what is ZS? ZS is RA plus JXS. Do we have RA? 0.5. So from here XS, this is equal to root over ZS square minus RA square. So we have calculated ZS, we have RA as 0.5, 3.175 whole square minus 0.5 whole square. So from here XS is 3.1357 ohm. All right. So next is what? We need to calculate magnitude of EF. So we have a generalized expression in case of generator as VT cos phi plus IA RA whole square plus VT sin phi plus IA XS whole square. Done. So VT is this is given as 2200 by root 3. Cos phi is what? Let me check once. 0.8. 0.8. IA is, under that particular condition we need to calculate the voltage regulation at full load. So the full load current we have already calculated as 200. 200 RA is 0.5 whole square plus VT sin phi 2200 divided by root 3. Sin phi is 0.6 this time plus IA is 200 and XS we have calculated as 1357 whole square. So from here EF value that we get is 1782.06 volt. All right. So percentage VR, this is equal to 1782.06 minus 2200 divided by root 3, 2200 divided by root 3 into 100%. So from here you will get 40.3%. So this I already knew from the beginning that whenever the lagging power factor is given, the voltage regulation will going to be positive. Done? Clear everybody? Shall we move ahead? Okay. This is the next question. The two generators rated 500 megawatt and 600 megawatt are operating in parallel. The characteristic of the generator are 4% and 5%. The droop characteristics 4% and 5% respectively with respect to full load. Assuming that the generator are operating at 60 Hz at no load, how a load of 1100 megawatt should be shared between them and the system frequency at this load. So ABCD option is given to us. We need to find the frequency and the current of the respective generators. All right. Now look at here. Whenever you will see the question related to the droop characteristic, then definitely you will have to find the one equation. So for machine 1, I will let you know what is that equation. All right. So for machine 1, this droop is equal to what basically? Droop is equal to no load frequency minus full load frequency divided by. Now, the denominator can be taken with respect to no load or with respect to full load. Means any of the two value can be taken as a reference. So in the question it is mentioned, it is already mentioned that these are with respect to full load. So we need to take here FL1. So this is what? Percentage drop. Now for the machine 1, this is given as 4%. So 0.04, this is equal to FNL minus no load I think given in the question as 60 minus F full load 1 divided by F full load 1. So from here you will get FL1 equal to, let me write it directly, 57.7 Hertz. All right. And the full load power for the machine 1, this is equal to, I think 500, this is given 600 megawatt. Done. Now for machine 2, this percentage drop, this will become droop. This is no load frequency minus full load frequency for machine 2 divided by full load frequency for machine 2 into 100%. So this is given as 5%. So 0.05, this is equal to FNL is 60 minus FL2 whole divided by FL2. So from here FL2, this will equal to, let me write the number directly, 57.143 Hertz, and PFL2, this is given as 600 megawatt. Done? Clear? Clear everybody? Now what next? We have one information which is given in the question. P1 plus P2, this is equal to 1100 megawatt. This is given in the question, na? Yeah, P1 and P2, this is given in the question. Clear? Now what is this F1? What is this F1? Okay, see here everybody. Let us take this axis as a frequency and this as the real power. Okay, so droop characteristic means your frequency is decreasing from no load to some certain value, like this. All right, like this. So this is given as 4% for machine 1, you can say 4% for machine 1. All right, so this is not required here. Now let us take this point as P full load, P full load, and your machine is operating, let us say some, for full load, your machine is operating at a full load frequency of FL. But this is not a general case. This is not the general case. Means it is not always true that your machine is operating at a full load. The machine can operate at less than the full load value. So let us take at less than full load, matlab, let us take here it is operating. Now at this point, this machine is generating a power P, at a frequency F. At a frequency F. So no load frequency is given in the question. Full load frequency is also given in the question. This PFL, full load power, is also given in the question. F and P here are unknown. F and P here are unknown. So how to find this value? This point is this point is 0. So see, this angle theta and this angle is also theta. So tan theta is what basically? Tan theta, can I say F NL minus F whole divided by P, perpendicular divided by base. What next? This is equal to, for this triangle, F NL minus F full load whole divided by P FL. Okay, clear? So let us find P from here. From here, P will be equal to P no load minus F upon P no load minus F full load times P full load. All right, so let me add one page here. So this is the generalized expression for any particular power that the machine is giving. So if this is P1, your full load frequency you will have to take for the first machine, and here full load power will be taken for the first machine. So substitute here. So this will be equal to no load minus F whole divided by no load minus for first machine, and here P full load for first machine, plus for P2 F no load minus this frequency is unknown, F no load minus F full load for machine 2 into P full load for machine 2. This is equal to 110. So no load is given as 60 minus F is unknown. 60 minus FL1 we have calculated as 57.7 into 500 plus 60 minus F is unknown, 60 minus 57.143 into 600, this is equal to 1100. We have one unknown here. So from here F equal to 57.42 hertz. So calculate, we have only one unknown here. You will going to get 57.42 hertz. All right. So this is P1 equation, na? This part. So from here P1 will substitute this F value here. You will get P1 as 559.5 megawatt and P2, this is equal to total power, which is 1100 minus P1, 559.5 megawatt. So this is equal to 540.5 megawatt. This is given in option A. Done. Otherwise, you can also get the P2 value from this expression. All right. So let us move ahead with the next question. This is the next question in our league. So again, this is a question. Sorry, this is a question from the parallel operation, which is MSQ type. Now read the question. Two 550 kVA alternator operates in parallel to supply the following loads. First is 250 kilowatt at 0.6 power factor lagging and 100 kilowatt at 0.5 power factor leading. One machine is supplying 200 kilowatt at 0.9 power factor lagging. The power factor of the machine of the other machine is. All right. So I need to find what is the power factor, and that power factor is leading or lagging. That we need to calculate. Now look at here. This is the circuit diagram of the two generators operating in a parallel, which is supplying the load 1 and load 2. Let us take this as machine 1. Machine, I hope this is visible now. This is generator 1, or you can say machine 1, and this is machine 2. All right. So do we have data here? For the machine 1, it is given that it is taking 200 kilowatt. It is supplying 200 kilowatt at 0.9 lag. Guys, please be alert here, because definitely we will going to see at least one question in GATE exam 2023. This is very important. This is very, very important, this topic from the synchronous machine. All right. For the second machine, we need to calculate the power factor. All right. So let us leave that part as of now. Load 1 is given as 250 kilowatt, 0.6 lag, and load 2 is 100 kilowatt, and this is at 0.5 lead. Okay, done. Now one thing for sure, the reactive power, sorry, not a reactive power, the complex power supplied by both the generator is equal to the complex load power. Means whatever complex power that are being generated by the alternator, that will be equal to the load complex power. Am I clear? So let us take here, this machine is supplying the complex power S1. Star is what? Complex. And this machine 2, S2 complex. This is visible, na? S2 complex. And this load is taking the complex power SL1 complex, and this is taking SL2 complex. Done. So definitely I can write here S1 complex plus S2 complex, this is equal to SL1 complex plus SL2 complex. In any machine, this point or this equation is valid. In any machine, the complex power generated is equal to complex power taken at the load, considering the losses. All right. So moving ahead, I need to calculate the complex power. Now look at here. for the machine 1, this is P1 which is 200 kilowatt, and the power factor cos phi 1, let us take, for this machine 1 is 0.9 lag. So from here phi 1 is what? Phi 1 is what? Cos inverse 0.9. What is cos inverse 0.9? This is 25.842 degree. Done. So here look at everybody. This P is what? S into cos phi, na? S into cos phi. But for the machine 1, let me take the subscript 1, S1, phi 1. So can I say S1 is equal to P1 by cos phi 1. So we have P1 value, cos phi 1 value. So from here P1 by cos phi 1, this is equal to 222.22. 222.22. But this is what? S1. This is the apparent power. This is a apparent power. But in complex, this S1 is what? P1 plus JQ1. Here plus is for leading. Sorry, for lagging. The plus J is taken for the lagging power factor. All right. So S1 is now, or you can say the S1 complex is basically what? 200 means magnitude of S1 at an angle S1. So this is equal to 222.22 at an angle 25.842. Now we need to take a negative sign or positive sign. We need to take a negative sign or positive sign. We need to take a positive sign for lagging, as it is written here. As it is written here. If you find the angle from here, na, S1 angle will be what here? Angle S1. This is equal to, sorry, let me write with different color. Angle S1 is equal to tan inverse of imaginary part divided by real part. So for the lagging power factor, you will have to take the angle of S as a positive for the lagging, and this is complex power. In the same way, if you find for machines, for the load, let us take here SL1 complex. SL1 complex. So I am writing it directly. I hope this is clear. Means in the same way we will going to calculate for SL1 and SL2. All right. So let me write it directly. This will become 416.67 at an angle. I think this is kVA, na? This part, this is kilowatt. So this will become kVA. This is become kVA. All right. And plus P is for lagging power factor. All right. So 416.6, here we will get the angle 53.13 degree. Again, the reason is same. Cos inverse 0.6 is 53.13 and the load is lagging. So we have positive sign. And SL2, this is equal to what? We have a leading load. So this will become P1 which is 100 divided by cos phi which is 0.5. So this will become, let me write it directly, this will become 200 at an angle. Cos inverse 0.5 is what? 60 degree. 60 degree. But this time the load is leading. So we need to put negative sign. Done. Why negative sign? For leading load. Or for leading power factor, you can say. For leading power factor. Done. So S1 conjugate plus S2 conjugate, which is equal to SL1 conjugate plus SL2 conjugate. Substitute all value, you will get S2 conjugate as equal to, let me write it directly, 162.8 at an angle 22.87. So since angle is positive, so power factor will be cos of 22.87. This is equal to 0.92, and due to positive we have lag. Done. It is clear. So please go through the question once again. Once the video will going to be uploaded, definitely you will going to have the concept. All right. So moving ahead with the next question, that is this one. Okay, just a second. All right, which is this one. A 400 volt 3-phase delta connected synchronous motor has an excitation EMF. So this time we have synchronous motor. Please do not get confused, because we have seen n means 5 to 6, nearly 5 to 6 question for the synchronous generator. All right. So this is the question from the synchronous motor. Has an excitation EMF of 600 and synchronous impedance per phase as 0.3 plus J6. Calculate the efficiency and the power factor when the machine is developing maximum gross mechanical power, assuming friction and windage losses as 2.4. So here we have VT, this is line voltage, this is EF, this is ZS, and what else? This is friction and windage losses. So basically this is rotational loss, P rotational loss. So how to calculate this one, yaar? So let me draw the diagram first. This is for synchronous motor. Take the reference terminal as VT at an angle 0 degree. This is armature resistance, this is synchronous reactance, and this is EMF at an angle minus del. So this E is what? This is magnitude. Please do not take it as a vector, sorry, as a phasor. This is not the phasor, this is magnitude of E at an angle minus del. So this R, and the current here is IA. All right. So this is what? E bar, and this is VT bar. Now, in the question it is given that the machine is developing the maximum gross power. Okay, maximum gross mechanical power means the power is taken at a mechanical in a mechanical direction. So the mechanical is what? Shaft only. So let us calculate the power equation at the shaft. Okay. So P mechanical, which is equal to P develop, means this power is generating inside the machine. So this is equal to EF, or you can say, let me write it E bar into IA bar, means this current is entering here, na? So this is E at an angle minus, sorry, conjugate, E at an angle minus del. What is IA? VT at an angle 0 minus E at an angle minus del, whole divided by magnitude of ZS at an angle theta S. So this is what basically? This is ZS. So ZS is magnitude of ZS at an angle theta S, which is root over RA square plus XS square, and theta S is what? Tan inverse XS by RA. Done. And the conjugate sign. So from here we have E VT by ZS at an angle theta S minus del minus EE square whole divided by ZS at an angle theta S. Is it correct now? But okay, this is S develop. This is S develop. Now for P develop, take the cos term because your active power is what? Cos term, na? So E Vt by Zs cos of theta s minus del minus E square by Zs cos theta s. Done. Now this P develop is what? P mechanical. All right. Now if this power, or you can say if P mechanical is maximum, then P develop max. So implies that from here, implies that this power can only be maximum when this part is maximum. This part is maximum. Why I am saying this part is maximum? Because this all part are constant. Theta is constant, E Zs are constant, E Vt and Zs are constant. Here del is variable. So this part is only maximum if this cos theta s minus del will be 1. So this will be 1 when this angle is 0. This angle is 0. Done. So P develop is maximum. This implies your del is equal to theta s. Okay. So theta s is what? Theta s, this is angle between impedance. Okay. This is given in the question. This is XS and this is RA. 0.3 plus J6. So 6 divided by 0.3. So this is equal to, or let me write here. (87.1376 degree). So at this angle, at this load angle, your synchronous machine will develop a maximum power. Done. All right. So what I need to calculate? I need to calculate efficiency, na? Or efficiency and the power factor. Okay. So P develop maximum, this is equal to what? This is equal to EF is given, which is 600. Vt is 400. Zs, this is magnitude of Zs. Take the magnitude of root over 3, magnitude of this, you will going to get 6.0075. And for the maximum, theta is equal to del s minus EF square. So EF is 400, na, I guess. Let me check. Sorry, EF is 600. EF is 600. So 600 square whole divided by 6.0075 into cos theta s. So resistance 0.3 divided by root over 0.3 ka square plus 6 ka square. Resistance and reactance. So cos theta is what? Resistance by total impedance. So this is cos theta. So when you solve this, you will get this value as 110.985 kilowatt. But this is 3-phase power. How? This is line voltage. This is line voltage. These all are line voltage. So whatever power you are getting, that will be the line power. Am I clear? Done. What next? Do we have a current IA? Efficiency we need to calculate. So input power and output power we require, na? So for that I require IA, and power factor we need to calculate. So how to calculate IA? So look at here, IA ZS, or we can write from this diagram, Vt at an angle 0 degree. This is equal to EF at an angle minus del plus IA ZS at an angle. This will be equal to theta S plus minus phi. So this I and ZS are magnitude. EF, this I have taken E. All right. E and EF both are same here. All right. So IA ZS at an angle theta S plus minus phi. This is equal to Vt at an angle 0 minus E at an angle minus del. So take the magnitude. So if you take the magnitude here, you will be having Vt square minus E square, plus E square minus 2 Vt E cos del. From the parallelogram theorem, we will have this value. So Zs we have magnitude, Vt we have, E we have, and del is what? Theta s. So all value we have. So from here I can directly find the IA value as 117.23 ampere. So the calculation part I have left for you. We have all values. Just substitute all values. This is what? Sorry. This is what? This equation is per phase. This is per phase impedance. So the equation is of per phase. Am I clear? So what next? So P shaft, this is equal to, means the power which is reaching to the shaft. The power which is reaching to the shaft is what? P developed at maximum condition, means at maximum developed power we need to calculate, minus rotational loss. So P developed that we have calculated 110.985 minus, and rotational is given in the question na 2.4 kilowatt. 2.4 kilowatt. So this will be equal to 108.585 kilowatt. All right. So this is the power which is reaching at the shaft, means this is the output power. This is the output power that we are getting. All right. So what is the input power then? What is the input power then? Please let me know what is the input power here. Now see the diagram. Shaft actually means we have shaft here like this. Okay, and exactly at this point, we are getting this power. We are getting where it is, just a second. This power, we are getting this power, and P develop maximum is what? We are getting here. So this is P develop max, and here this is P shaft.